All right, so following up with those last couple of examples, I should probably double back and actually give you the definitions of those two different types of quantifiers that we saw. The first one that we saw is referred to as this universal quantifier, and this thing is going to emerge anytime I have this statement that says for every or some version of that. And I like to think about these universal quantifiers as being some really big giant looping structure. What's going to happen in all these different types of statements is you're going to have this little sentence or this little predicate, this kind of information about what's going on. But you're also going to have some information on what are your testable elements. What's going to happen in this universal quantifier is that you're going to have to test against every single element in whatever set you're working with. For example, the first one that we saw was of the form for all x in the real numbers. So in this case, this big set that I'm working with is the massive set of all possible real numbers. This thing is horribly large. It is uncountably large, in fact. What we're going to have to do is we're going to have to test every single element in this thing against this sentence that claims x squared is greater than 0. If I can find just one thing that breaks this, I know that this thing is actually going to be a false statement. If I don't see something that breaks it, I might in fact actually have a true statement, and then I actually have to go ahead and try to write a proof for that thing. And there'll be more about that kind of in coming videos and things like that as well. But in this case, we actually have that this is going to be a false statement, and the reason it's going to be false is because I can find a real number that has the property that when I square it, it is not greater than 0. That example is going to actually be 0. I know 0 is a real number, but 0 squared is 0, which is not strictly greater than 0 because it's equal. If I actually would have included equality in that thing, we would have had that this is actually a true statement. But for now, because we are missing that fact, we do in fact have that this is false. So like I said, if this is going to be true, it must be true for every single real number input. If I can find just one counter example, that thing is going to be false. Okay, so as with everything, we have multiple ways to represent these different types of statements. So the first one that we have written up above is actually kind of the formal symbolic version of this thing. Underneath it is actually a couple different ways you can express this in kind of a slightly more plain general English phrase. The one right below it is probably the first way you'd write this thing down, this idea of for every real number x, I'm going to have that x squared is greater than 0. You could also put this a slightly more kind of manipulated way, the idea that the square of every real number is greater than 0, or you could even write this thing down as a conditional, the idea that if x is a real number, then x squared is greater than 0. So as always, kind of just get practice working with rewriting these things in a couple different forms. A lot of times you're going to be given something like this, and you're going to try to write this thing in symbolic form, because the symbolic form doesn't kind of have any of that awkwardness that the English language sometimes does. It's just, here's what it is, now go with it. Okay, so on the flip side of all of this is going to be this notion of an existential quantifier. And this is going to come up anytime you see this phrase that says that there exists. So in comparison, the last one was you had to test against every single thing, and I had to be true in every single example. In the world of existence, all I need is I need to find at least one special object that's going to satisfy my little sentence or this little predicate. So you can kind of see the two little extremes. In this case, I just need to find at least one that does the trick. So in this case, my statement's going to be, there exists an x in the real numbers such that x squared is going to equal 5. So this is not saying that every single number is going to have this property, but can I at least find one? In this case, this is actually going to be true. And the reason why it's true is, well, you could think about x being the square root of 5. That's going to be a nice real number. That thing is not an integer. It's not even a rational number, but it is in fact a real number. And it has this very special property that when you square it, it kicks out a 5. It is, however, not the only one. We obviously know that the negative square root of 5 is also going to be a real number, and it also has that property. So it's not saying anything about the idea that there has to only be one. That's going to come up when we start talking about uniqueness. But for now, this is just going to be a notion of there is at least one that does the trick. All right, so as with up above, we actually have multiple ways to represent this object. The idea that I can convert this to the very vanilla version that just simply says there exists a real number x such that x squared is equal to 5. That's actually how you would take this kind of logic version and just convert this thing down into a sentence. That's probably the easiest way to represent this thing. But there are alternative ways as well. You could say that there exists a real number whose square equals 5. You could just put that actually in words, or you could just simply say x squared equals 5 for some real number x. I don't really like that last one. I don't like starting a sentence with some kind of mathematical object. It looks really bad to kind of represent these things. So that's something you probably actually want to avoid. But in terms of this existential stuff, it does actually work. But like I said, it's not great to represent things like that.